Have you ever wondered what actually happens in the instant you press a button to take a photo? You hear a click, and a moment that was just happening is suddenly frozen on your screen, ready to be shared and revisited forever. But how? How does a machine, a small box of glass and metal, translate the light from a sunset or the smile on a friend's face into a digital file? It feels like magic, but it's actually one of the most brilliant feats of everyday engineering. Think about the real world around you. It's not made of pixels or data. It's a continuous flow of light, colors, and shadows. There are infinite shades of blue in the sky and countless textures on the bark of a tree. The problem, for the engineers who designed the first digital cameras, was immense. How do you capture this infinite analog world and convert it into a finite digital format? How do you teach a machine to see? It's a fundamental conflict between reality and data. Reality is smooth and seamless, while data is made of distinct, countable pieces. Solving this problem required a deep understanding of light itself. So let's pull back the curtain on that split-second process. We're going to explore the hidden world inside your camera, a world that operates faster than the blink of an eye to perform its incredible task. It all begins with light. Everything you see is thanks to tiny particles of light called photons. These photons travel from a light source, like the sun, bounce off objects around you, and enter your eye. A camera works on the same principle. When you point your camera at something, you are really just aiming a funnel to collect these bouncing photons. That funnel is the camera's lens. Its job is to gather the light from your scene and focus it precisely onto a single point. For a brief moment, when you press the button, a shutter inside the camera opens. This is the click you hear. It's like opening a window to let light flood into a dark room, but only for a fraction of a second. That light doesn't just splash around inside. It's directed onto the most important part of a digital camera, the image sensor. This sensor is the digital equivalent of film. It's the heart of the entire process. This sensor is a small chip, about the size of your thumbnail, covered in a grid of millions of microscopic light detectors. Each tiny detector is called a photosite, but we know it by a more common name, a pixel. Think of each pixel as a tiny empty bucket. When the shutter opens, photons from your scene pour into this grid of buckets. A brighter part of the scene sends more photons, and a darker part sends fewer. So a pixel's only job is to count how many photons hit it during that brief moment the shutter is open. But this presents a new problem. A bucket can tell you how much water it has, but it can't tell you the water's color. In the same way, a basic pixel is colorblind. It can only measure the total amount of light it received, which translates to brightness. A picture with only this information would be black and white. So how do we get the vibrant reds, greens, and blues of a photograph? Engineers came up with an ingenious solution. They placed a microscopic color filter over each individual pixel. This filter pattern, called a Bayer filter, assigns one color to each pixel. Some pixels are given a tiny red filter, allowing only red light to pass through. Others get a green filter, and the rest get a blue filter. Your camera sensor is therefore a mosaic of red, green, and blue pixels. It never captures the true color at any single point. Instead, it captures the brightness of red in one spot, the brightness of green in the spot next to it, and so on. Interestingly, this filter isn't an even mix. It usually contains 50% green filters, 25% red, and 25% blue. This is because our own eyes are most sensitive to green light, and mimicking this makes the final image feel more natural to us. So now we have millions of pixels, each holding a measurement of a single color's brightness. This measurement isn't a number yet, it's a tiny electrical charge. The more photons a pixel collected, the stronger its electrical charge. The next step is to read this information. The camera's brain, the image processor, scans the entire grid, one pixel at a time, measuring the electrical charge from each. This creates a long stream of analog electrical signals which are smooth and continuous, just like the real world. But computers don't understand smooth. They only understand numbers. This is where a crucial component called an analog to digital converter, or ADC, comes in. Its job is to take the smooth electrical signal from each pixel and convert it into a discrete number. A weak signal from a dark part of the image might become a low number, like 10. A very strong signal from a bright white area might become a high number, like 4,000. Suddenly, our image is being translated into the language of mathematics. Now the camera has a massive list of numbers, but remember, each pixel only recorded one color. The red pixel has no blue or green information. The blue pixel has no red or green. The camera now has to perform an incredibly sophisticated guessing game. This process is called demosaicing. The camera's processor looks at a red pixel, then looks at the blue and green pixels around it. Based on the values of its neighbors, it makes an educated guess about what the blue and green values for that red pixel should have been. It does this for every single pixel on the sensor. Imagine a 20 megapixel camera. That means this process of guessing the two missing colors is performed 20 million times, all in a fraction of a second. This is all handled by the camera's powerful brain, the image signal processor, or ISP. This is a dedicated chip that does much more than just guess colors. The ISP acts like a professional photo editor, but one that works almost instantaneously. It analyzes the raw data from the sensor and begins to clean it up. It adjusts the overall color balance to make sure whites look truly white, not yellowish or bluish. This is called setting the white balance. It also works to reduce something called noise in very dark areas of a photo. The electrical signals are weak and can be random, creating a grainy look. The ISP intelligently smooths these areas out. It also enhances the sharpness of the image. The processor looks for edges between light and dark areas, and subtly increases the contrast along those lines, making the picture appear crisper and more detailed. Every camera manufacturer has its own secret recipe, its own special algorithms that the ISP uses to process the image. This is why a photo of the same scene can look slightly different when taken with two different brands of cameras. One camera might prefer more vibrant, saturated colors, while another might aim for a more natural and muted look. That look is programmed directly into the image processor. After all this processing, color guessing, white balancing, noise reduction, and sharpening, we finally have something that resembles a photograph. It's a complete map of millions of pixels, each with its own specific red, green, and blue value. But there's one last problem. File size. An uncompressed map of all this color data for a single photo would be enormous. It would fill up your phone's memory in no time. So the final step is compression. The processor cleverly squashes the data into a much smaller package like a JPEG file. It does this by looking for large areas of similar color and simplifying the information. For example, instead of saying, this pixel is blue, this pixel is blue, this pixel is blue, it can just say, the next 100 pixels are all this specific shade of blue. This saves a huge amount of space. And with that, the process is complete. A slice of reality made of light has been converted into a grid of numbers, processed, and packaged into a neat little file. All of this happens between the moment you press the button and the moment the picture appears on your screen. The core insight here is that a digital photograph is not a magical copy of a moment. It is an interpretation. It's a translation from the language of physics into the language of mathematics. Every single picture you have ever seen on a screen is, at its most fundamental level, just a giant organized grid of numbers. The image processor's job is to turn those numbers into an image that our brain perceives as beautiful, sharp, and true to life. The camera doesn't just see the world, it measures it. It takes an infinitely complex scene and samples it at millions of discrete points, turning flowing reality into a structured spreadsheet of data. The art of photography, then, is built on a foundation of pure mathematics and engineering. The technology disappears so that the moment can shine through. Engineers solved the problem of capturing an analog world by breaking it down into millions of tiny, manageable pieces. They created a system that funnels light, measures it, translates it into numbers, and then intelligently reconstructs it. This solution is a breathtaking ballet of physics, electronics, and software. It's a testament to human ingenuity, a process that happens billions of times a day around the world, hidden inside the devices we carry in our pockets. So the next time you take a picture, remember what's happening. You aren't just capturing a moment. You are commanding millions of tiny electronic artists to paint a masterpiece with numbers, all in the blink of an eye.